Hello, this is Axial Loading Statically Indeterminate Problems. Okay, so in this problem I'm going to go through a special scenario, a special case, and it's one that you'll see fairly commonly. It's a beam that is going to undergo some loading, and it's not quite clamped on both ends. However, there's a little gap. So what's going to happen is the force is going to act on this beam. It's going to elongate, and at some point it's going to fill up that gap and become clamped on both ends, making it an indeterminate problem. So as you've seen in the other indeterminate problems, there's a four-step process, or 3 or 4-step, depending on how you break it up, process on how to approach with them. And the good news is you can more or less apply the same exact approach to this special case. So just looking at the problem that I have set up, it's a fairly simple one. I really want to just show you how to work with a gap and work through it. So it's a uniform cylindrical beam. It's, let's see, what is that, 1.1 meters long, and it has diameter, area, it's steel. Most important thing is a 1 millimeter gap. So let's go ahead and start putting this in the program and work from there. So as far as putting it in, you can just kind of ignore that there's a gap for now. It's all uniform geometry, so we can just treat it as one segment. Okay, so it's 1.1 long, outer diameter 5 millimeters, steel 200 gigapascals. Okay, that solves out to a very, very small area. And as far as forces go, we just have the one applied, 20 kilonewtons at 400 millimeters. So it's 1. Location, remember, bring that into meters, so 0.4 meters. And it's 20 kilonewtons in tension with regard to the left end. Okay. And as you'll see, there's an option here, left and right clamp, and there's a gap box. And we can put that in. It's 1 millimeter, so there we go, let's draw it. So just like with the other indeterminate problems, we have our several step process. And it's basically the same. First time you remove the right clamp, solve it out. Second time, remove the right clamp, put a unit force on the right end. And then with those two net elongations, you can solve for the force of the right clamp. However, solving for that force, because there's a gap, there's going to be a different equation that you use. And when we get to it, you'll see what that equation is. It's nothing to be worried of. It's just a little bit different calculation. Otherwise, same exact process all the way through. So let's go ahead and start solving. Yep, it pops up here kind of running you through the process. Okay, so let's move on to step 1. Now it wants you to put in the elongations of section 1 of either section, so section 2 first and then section 1. However, when you move the right clamp, there's no loads on this section 2. So straight up, 0 force, 0 reactionary force, 0 stress, 0 elongation. So all of the calculations I have here are analyzing section 1. And section 1, you have this 20 kilonewtons, the opposite reaction, and so on. Fairly easy. Let's go ahead and put in that elongation. Okay. So on to step 2. And just remember, it saves the different net elongations on here so that you can view them later. So on to the next step. So now we have a 1 Newton force in tension applied to the very end. And notice it just wants you to enter the net elongation for the entire segment all at once. So even though I have this all calculated out, you don't really need the stresses. You could just, treat it as one section and just be done with it. However, I always just keep on going through analyzing section by section, as I always have, just for the sake of keeping it consistent. So as you can see, the elongations I have for each section, you have to add them together, which I have here, which is the net. And let's apply that now. Okay, so as soon as you do that, you have those 2 elongations, then the program solves for the force at the right clamp for you. However, let's look at the equation that it uses to get that. So similar to how it was before, it's the net elongation of 1 divided by net elongation of 2. However, this time you're factoring in the gap distance, and that's all there is to it, really. You can see, they have the same value as me, just rounded a little bit different. But now that you have the force on the right end, just like the others, it's now become, finally, a determinate problem that you can just go through your final solution with. So let's go ahead and do that. And we can solve this. So, yep, on the right end, there's that reactionary force of the right clamp. At this point, we're ignoring the gap. And that's basically it, just the same calculations as always. So I'm just going to go ahead and put these in. Okay, now for section 1. Looks like I have an error here. Let me check it out quick. Okay, looks like I just entered in that value wrong for the first force. And that's it. That's all there is to it. So basically you can approach these gap problems more or less the same exact way as you have for the other indeterminate problems. It's just when you calculate the force of the right clamp, you just subtract, go back to it, you just subtract net elongation of step 1, subtract the gap distance from that, and you will be able to find the force in the right clamp.